Hey everyone, welcome to another Explainer. Today we're digging into some really fascinating recent notes from author Ang. We're talking all about modernizing and refining code. Specifically, how just a handful of precise syntactic tweaks can literally transform a codebase from a totally tangled mess into something, well, elegant and readable. Okay, let's dive into this.
So, Ang kicks things off with this quote. Even though I'm writing Haskell almost daily for my pet project, I still struggle to remember much of the syntax. Honestly, how relatable is that? It just goes to show even programmers who are literally in the trenches coding every single day hit this wall where the syntax just feels overwhelming. If you've ever felt like you're fighting the language instead of actually building with it, you are definitely not alone.
And actually, there's a very specific reason for that struggle. It boils down to TMTOWTDI. That stands for there's more than one way to do it. Now, this is a philosophy famously inherited from the Perl programming language, but as Ang points out, Haskell suffers from this exact same issue. See, when there are just way too many ways to express the exact same piece of logic, you end up with this inconsistent alphabet soup across your entire codebase. It makes everything confusing, hard to read, and notoriously difficult to memorize.
Section 1. Refactoring with as patterns, moving away from getter functions.
To really grasp this, let's break down the mechanical steps of an as pattern. Think of it kind of like holding a box while simultaneously grabbing exactly what you need from inside it. Step 1. You use the @ symbol to refer to a whole data type, in this case, args. Step 2. You reach inside that data type at the exact same time. And Step 3. You bind specific fields, like input path, directly to variables. It's a game changer because it allows you to reference the entire structure while plucking out exact elements in a single motion. No more repeatedly unpacking and repacking the data.
Let's actually see that in action. Over on the left, we've got the before state. Just look at those getter functions, input path args and output format args. They are super repetitive and, frankly, visually noisy. But now, check out the after state on the right. By utilizing the @ symbol, we establish args at and simultaneously grab what we need. Input path equals path and output format equals fempt. And this brilliantly illustrates the glow up. It's so much more direct.
Now, the practical payoff here is absolutely massive. By binding input path to the simple variable path and output format to FMT right up front, the execution code that follows just becomes significantly cleaner. You don't have to repeatedly call those clunky getter functions every single time you want to use the data. The logic of your program actually shines through because all that syntactic noise has been stripped away. What you really want to take away from this is that a tiny, upfront change in how you declare your variables leads to cascading readability improvements throughout your entire function.
Section 2. Named-record-decomposition, ditching brittle positional matching.
Now, what's really interesting about this next technique is how it fundamentally future-proofs your code. Let's contrast the old with the new again. On the left is the brittle approach, positional pattern matching. You're relying entirely on the strict, exact order of fields, using all those underscores just to ignore the rest. It's a bit of a mess. But on the right, we have the named approach. Here, we explicitly name exactly what we want, like input path and verbosity, and we just ignore the rest naturally. Much better, right?
Let's summarize exactly why this named record matching is so superior. First off, it completely eliminates that brittle positional matching we just looked at. Second, and this is absolutely crucial, it makes your code immune to field reordering. If someone comes along 6 months from now and changes the order of the fields inside the args data type, your code won't break. You no longer have to worry about the specific ordering of fields. And finally, it instantly clarifies your variable names right at the point of entry. It's just a massive win all around.
Section 3. The Elixir standard, the gold standard for syntax.
So, stepping back a bit, when it comes to pattern matching, Ang has a very clear benchmark for what great syntax looks like, and that is Elixir. Inheriting its foundation from Erlang, Elixir arguably has the absolute best syntactic support of any programming language out there. It provides completely unmatched productivity and flexibility when you're parsing data structures.
But, yeah, there's always a catch, isn't there? If Elixir is so amazing, why not just use it for everything? Well, it's simple. Elixir just isn't built for low-level systems programming. If you're in a situation where you need direct control over memory and bare metal performance, Elixir becomes much less enjoyable, and honestly, it's often totally inappropriate for the job.
Section 4. A dream systems language, building the ultimate Frankenstein. This limitation begs a really fascinating question. What if we built the ultimate Frankenstein systems language? Just imagine for a second splicing the DNA of 3 distinct languages together.
From Elixir, we'd take the abstract syntax tree and that beautiful, flexible pattern-matching syntax we talked about. Then, from Rust, we'd graft on the rigorous type system and memory safety, but crucially, without a garbage collector. And finally, from Go, we inject raw, systems-level, bare metal performance. Combining these three, it would literally solve the alphabet soup and the performance problems in one fell swoop.
Now, obviously, building a brand new systems language from scratch is a pretty monumental task. So Ang proposes a slightly simpler alternative. What if we just created a new Haskell language extension? Basically, we could forge a new dialect that simply imports Elixir's syntax directly into the Haskell ecosystem. You'd keep all that underlying power of Haskell, but you'd swap out the messy interface for a clean, flexible one.
And this brings us to a final, really provocative thought. In the age of artificial intelligence and large language models, could you actually build this dream systems language today? And suggests that with AI assistance, creating this Frankenstein language or even a new Haskell dialect is a totally doable project right now. So, what do you think? Are we on the cusp of a golden age of custom, perfectly tailored programming languages? It's definitely something to think about next time you find yourself wrestling with messy syntax. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you in the next one.